then we're good to go. All right. So what you're seeing right now is the state that we left off after episode 5 last week. So we'll just open up the code. You see it's still on the episode 5 branch that I checked in, and you can check it out. A link to it is in my show notes on my blog from last week. So let's open up our main file. So just maybe I increase the font size a bit more. So all the code is still in the main Elm file, by the way. So we're at 380 lines of code for what we already have. We can move the tile left and right. And like given the spacious layout of Elm code, like that's the opinionated way to lay it out from that comes with the Elm formatter. I think that's quite a reasonable lines of code count. Okay. So I think actually I haven't prepared anything from for this episode, so I don't know how I'm going to approach the problem. So for me, the first point where I would look is basically now, okay, we're dropping the tile. So, and the way we implemented it, we can also quickly revisit that, is we added a subscription. So we have two subscriptions. The one is the time every, that's like the timeout function in JavaScript, where we fire an event every 1000 milliseconds, the gravity tick, and the other subscription is to register our key press events. So I would say, like, basically at the moment where we want to try to drop a tile, if something is under the tile already, then we cannot drop it, and it should be like baked into the current state of the board, because we have the separation. We have if we look at our model again, or our board type alias model, we have the separation between the current piece and the board, and this comes in really handy in several places. So basically, once we cannot drop the current tile any further, or piece further down, we want to become a part of the current board. So as I mentioned, the time where I think that should happen is when we drop the current piece. So naturally, and that happens in every 1000 milliseconds with this gravity tick message. So I will look where we process this. That would be here. So here we calculate a new state of our model, and let's revisit. It's a short function, so I'm sure we can just analyze quickly again what we did here. It's like the main expression that we return from this function is below the in keyword. Everything above is just local expressions, basically. So we're updating the current piece and use the dropped piece instead. The dropped piece is an updated version of the current piece, where we use it position and change it to, like, we don't modify the X position, but we drop it one row. And the next row, and this is the little hack that I mentioned in the beginning, is where I'm hard-coded that if the current row is 20 is 0, then I just reset it to 20. So actually what we are seeing is not several different pieces falling through, but it's actually the same piece that I just sent back to the bottom, to the top once it hits the bottom. So there are probably several ways to approach this. And when I was setting up my equipment, I thought a bit about how I want to approach this. So I think the most naive way, and that doesn't mean it is a bad way, and we can always refactor or improve, is like, I think the way a human would think about this, and I try to write my programs in a way that a human would describe a solution to the problem, because that makes it most likely that a human also understands the solution again, and since I'm most likely the human who has to understand this code again, I just want to keep it human friendly. So the way I think about it currently would be like, before dropping the piece, I calculate the tiles. So I think we made this distinction, or like these pieces or elements, I have to look it up how we call them, or how I call them, is I'm trying to calculate the new tiles that the current piece would like to occupy once it's dropped. And then I want to check in the board if all of those are free, and if that's the case, then I can safely drop the current piece. So yeah, I think like once we made this change, the name drop current piece is probably not entirely correct anymore, because in the case where we can not drop the piece, we have to bake it into the board and actually spawn a new piece. So the responsibility of this function, or what actually has to happen every second, is a bit more extended than initially described by this function name. But we can rename things. Refactoring stuff like this is really easy in the typed language, so we just worry about this later. So I would say we can just write our intended outcome. So I would say if can drop, then do what we did before, else spawn new or bake in. Now maybe we start with bake in piece, like, and with baking in I mean this process of converting the current to piece into a part of the board. And spawn new piece. Let's be very verbose here. Okay, so can drop should be a boolean, obviously. So I don't know, do we make this top level function right away? Yeah, maybe that helps us to, because like we can specify a signature, and or I mean we can also specify actually signatures in local expressions. So I can also say like can drop should be boolean. I never know, and like actually half of the language it's called boolean, in the other half it's called just bool. So let's have the compiler figure that out for us. He will nag us if that's the case. So current can drop. So what are the inputs to this function? I mean, actually, maybe we don't even need this to be a function. Yeah, we can keep the signature, but let's try to write down our algorithm in pseudocode. So, and we already have the drop piece, so that's a big plus. And I think we also had already a function that calculates the positions for us for the current piece. So I just search for positions here. Absolute tile positions. What does it do? Place piece on board. Oh, okay. So we actually already even have the function that we need to call to bake in the current piece into the board. So that will make things easier. And translate tile. Translate tile just takes a. Oh yeah, that's looks very handy. So I'll just copy this and put this here. So absolute tile positions. This is a, or maybe actually it's good that we have this pseudocode, but if also if we want to have meaningful feedback from the compiler, then we should maybe remove the pseudocode. So, and now it tells us here that expression defines xy. Oh yeah, xy is already defined, so we can actually throw this away. Let's see if this compiles. So this compiles again. Okay, and now what I wanted to show is how we can also use signatures for the local expressions to verify our assumptions about types. Like this is a translate type is a function, but we never wrote a type signature for that, and that's much more common for these local helper functions, basically. But nonetheless, it's possible, and it's just nice sometimes to get this early verification rather than just using this function somewhere and then get told by the compiler I cannot use it there because I expect that signature, but it has that signature and so on. So let's just create a local signature here, repeat the name, and it takes obviously a position, int, and it calculates another position. I mean, that's actually not that hard, but it's just... So we see like it compiles without errors. So this assumption was right. And we see we map this function over a list of tiles from the current piece. So it's safe to assume, oh, actually we can do it just here again. That's the thing that I was actually wanted to confirm, that this is a list of positions. I think do we have a type for position? Yes, we do. So that's great. So that's like, depending on where the current piece is, we will get like for each of these little squares its positions. And so we're calculating that on the current piece. But with my initial algorithm, I said I wanted to test the positions of the dropped piece. So instead of using the current piece, I will just replace the current piece, not with a dripped, but with a dropped piece. So now we have the positions of the single elements of the current piece if it would be dropped. And what I want to make sure now I just want to basically go through the current board, look up those positions and make sure all of them are empty. So, and I can write down how I want this expression to look in terms of types. So I would say we want to look up. Yeah, actually I have to look at, like I haven't worked with that in some time, so I'm not sure about the types in our board type. Our board is a list of rows, and a row, what is a row? A row is a list of field, and a field can be either empty or have a certain color. So I would say drop tile positions. Let's say dropped tiles are empty. Let's use this one for descriptive identifier. So we know we have to map over the absolute tile positions. I mean, and when I don't know exactly yet what the function does, and then I usually just choose a one-letter identifier that I then expand later on. So we know the function that will map over the tiles has to take one of the tile positions as parameters. So we know, let's call them tx and ty. And basically we want to make sure that look up on the board at position, or let's just call this pos, and we want this to be, we want to know if this is empty, basically. And I have a hunch we have a function to look up a certain tile on the board as well already. Do we have something that's called lookup? No. Let's just browse quickly through what we created so far. Update row, set fields, no. Init, no. More update, move piece, drop current piece. No, actually, I think place piece on board. Board view. Field view for row, no. Also view stuff, ff to color, field view. So actually this function doesn't exist yet, so I think that's a good opportunity. So we want to look up at a certain position, tx.ty, from a certain board. And yeah, I'm just going to write this out, or maybe actually I stick to my exercise of writing down the type signature first. So let's call it look up. We take a position and a board, and we return a bool. Yeah, I guess we can directly return a boolean if this field is empty. So let's call it, or maybe, no, let's call it, yeah, let's call it as empty. Oh, that's good. That's good. I think that will work. Is empty. So let's go back to our type definition of board. Here is a list of rows. So I'm not sure how we ordered our rows, but I will just assume the row with the number 0 is at the beginning. So that means if I want to look up what's in the 5th row, for example, then I can just ignore 4 rows. And the easiest way to ignore 4 elements from a list is the list drop function. Maybe I'm a bit more descriptive here. I'm just going to say, so the row that I want to look at is the row that comes after I dropped n-1 rows, basically. So I say list.head, and then I like what list of head for a list just gives me the first element of a list. So if we have the list of rows, I just drop or remove the rows that I'm not interested in, and then I'm taking the first list of whatever's left. So that's my row. And then we basically do the same thing for the columns, because a row is nothing more than a list of fields. So I would say like field equals list.head, the first element of the columns after I dropped the columns that I'm not interested in. tx. So, and then I should be able to say is empty, field equals empty. So let's try to put this into the placeholder that I created. So here we want to map, is empty about the absolute type positions. And that's doesn't really work well, because this empty is expected to be a function that only consumes one of the elements of the list that I'm passing here in, and we're passing a position and board, so that's not really nice. So actually I have to invert, and that's something that's particular, I would say, to functional programming. That's something I don't worry about so much in imperative programming language, but because you do this function combination, a lot of function composition and partial application, you sometimes just have to move around the order of the parameters for it to work out well for you. But there's also actually functions that do that for you, that will just invert the arguments. But since we are creating it specifically for this purpose, it's easier to just invert it in our definition. So instead of position board, we say board position. Have to invert the actual parameters as well. And this way we can now partially bind the board to the isEmpty function. So that means effectively by the partial application we are removing this first parameter, and then we end up with a nice function that takes only a position and returns a Boolean. So what we end up with, if we map over the absolute type position, is an array that contains Boolean true or false for each of them, and if each of them is empty, basically. Because we know if that's the case, then we can actually drop the piece. So, but obviously we're not done. I said in our pseudocode I wrote if can drop. So what is can drop really? Let's just expand on the pseudocode a bit more. Can drop basically means if all drop tiles are empty. That reads quite nicely with the verbose identifiers I chose. So that's it. And I think there are some nice helper functions for this actually in the list module already. Quickly not to the guide. We want to go to the documentation. Where's the I just Google for it. Elm list. Boom. So we have map, we have indexed map, that's all nice, filter. And I thought there's something like any. Yes, actually that's what I was looking for. So those are two functions that actually save some work for us. The all and the any are functions that basically can save us the calculating the result with a map and then asserting another thing on all or any of these. They're very descriptive. I think you get the gist. So instead of actually mapping, we can say directly all. So, and then we can just shortcut this to can drop is all is empty absolute type positions. So I think that looks quite nicely. We're not doing something with the result yet. I just want to make sure that the compiler is happy, and actually I'm pretty sure it's not happy, but we'll work our way up. I don't know if you want to take a guess on what's going wrong. If you look at the, like specifically this expression, there's a logical corner case that the Elm compiler or the Elm functions will help us discover or fix. And so let's reveal the big flaw in our logic. So it says is empty. There I made the Boolean error again. It complains about Booleans, so let's just call it bool. And now it says I cannot find a board variable. That's also fine, because I have destructured current piece here directly, but not board. So I will just add this. And now it says, oh, it's again. Okay, it's also not happy about this. Yeah, actually I can simplify this because it's a local function. I can directly access the board, so I don't even have to do my little partial binding trick here. Just going to remove this. Boom. Let's see. Now we're getting closer. We have to qualify the list all call here, so it knows from which module to take this. Okay, I cannot say 236. Let's put this into context. I'm just going to close this window here. Okay, so it says list head, list drop. Okay, yeah, I forgot. List drop takes actually a parameter on how many elements. Oh no, that's specified by, but from what is the question should I drop? So it should drop from the board, which is just a collection of rows. And here we have to drop it from the row. Okay. This board value is a board. Okay, I thought the board is just a list of row, but I have to revisit the type definition to find out what it actually is. Type alias board. Okay, I see what my mistake is. The board is not just an alias for a list of row. It's actually this record type. So I have to say board dot rows. And now we're finally getting to the point I actually wanted to make, which is it says this row value is a maybe row. But list drop needs the second argument to be a list A. Wait a minute. So let's look at this in context. Oops, 239. This is when we're trying to drop TX columns from our row. This row, it says it should be a list from something. Yeah, obviously it should be a list of fields, right? But it's a maybe row. Why is it a maybe? So where does this expression come from? It's this row. So let's bring up the definition of row just to make sure that I correctly state what I'm expecting. What is a row? A row is defined down here. A row is a row is its own type. So we can, like, again, just bring up our little trick, define a local signature. That's what we want to have, or that's at least what I said it should be. And it says like, yeah, okay, you say you want to have a row, but it's really not. It's a maybe row. So wait, why it's a maybe? So what's assigned to row here is the return value of this function. So let's just go back into the documentation and see what it says. Like, and now this is revealing what I meant is like the types actually help us or help the compiler identify our logical flaws. Because if I try to take the first element of a list, I have to deal with the case that the list is empty. And the way that this is implemented in the standard library from Elm is that instead just returning an A from our list of A's, we're returning a maybe A. So in the undesirable case that we're returning that we're passing in an empty array, this function will return a nothing. So that's why we're actually having a maybe row here. So okay, yeah, I see it. I see. I understood. I learned. I will fix my type signature, maybe row. But now, of course, if I say drop something from a maybe, how the maybe doesn't really. I cannot pass it. Like if we can same for drop. Where's drop? Should be. I just find here, search here. So drop takes an int and a list of A, and like a maybe list of A obviously is not a list of A. So we have to first deal with that case. So let's prefix that with MB. I'm not sure if there's a better convention for that, but that's because I usually don't keep those inline type signatures just to keep my code a bit more concise. So to indicate that this is a maybe, I sometimes just would call it maybe row, because then I can do with a pattern matching here where I'm like case maybe row off, just row, and then this should work again. But now I also have to make up my mind what I actually want to do in the nothing case. So I would argue when we try to address a row, like when we try to find a piece in a row that doesn't exist, yeah. Like for example, if we go out of index with our ty here, then whatever field I'm trying to look up is definitely not empty. So the question is, okay, maybe again, little trick or self verification here is what do I want field to be? Field is, and I can already tell because I'm using head here again. This will probably also be a maybe field at best. So that really makes it easy for me to write the case in where I already didn't find the row. Then this will be nothing. So I would say argue at least that would fix our maybe problem in terms of heads and drops and lists. So let's see. Second argument of drop is not what I expect in 242. 242. Why is it not what you expect? This value is a row. Oh yeah, that's actually correct. So I just closed it, but we're going to revisit the type definition of row. Okay, I made the unfortunate choice when I wrote this type to make it a like this variant type. So I have to also, it's not that bad because I can easily pattern match, and this actually is, it has also an advantage. For example, I can now actually give a name to this list of fields which logically represents our columns. So that means also this reads a bit nicer after I renamed this. Okay, cool. On to the next error. So now the check where we actually test if the field is empty doesn't compile because it said like the left side of is maybe field, but the right side is field. So yeah, that's correct because after all, we just introduced explicitly that this result of this can be nothing, but it's also implicitly by this head call again here on the columns. So, but it's an easy fix because here again we can basically just write out the complete value, which is just empty. So if it's nothing, then obviously it's not empty. So, and woohoo, it compiles. So usually if we make our steps to be small enough and it compiles, that means we're really close to the solution. So let's revisit our pseudocode, or maybe even, yeah, maybe we just reactivate it. Unfortunately, like the comments are formatted really differently than normal code, so that sometimes messes up the indentation a bit. Okay, let's just, for the sake of this compiling, keep our intention again as a comment if can drop, then basically we continue with our current behavior, else we also just current behavior. So I want to take really small steps to always keep it compiling, so I don't have to, because the last loop of cleaning up this mess that I created here was a bit too long for my taste. So for actually something to change, like the smallest change in behavior that I want to see, I would argue is I want, if this piece drops to the bottom, I want it to stick there and to see a new piece being spawned. So that means I actually have to update two things. I have to obviously update the current piece for it to be a new one that's on the top, but I also have to bake in the current piece into the board. And as I discovered earlier, we already have a nice function for that. So I just have to discover it. Put piece, what was it called? I forgot the name. I think it was somewhere down below here. Let's see, field for view, more view functions. Place piece on board. Takes the current piece, takes a board and returns a version of the board where this piece is placed. So let's do this. Board equals place piece on board, current piece, and the current board. Okay, so I feel pretty confident that I called this function with the correct type. So I just close my little lookup window here. And now the question is, how do we get the new piece? And like we're doing this at initialization of the app already, that we create this new stone somewhere or piece somewhere. So I'm just going to reuse that code. Let's go to the top and search for the init function. Empty board, current piece. Okay, that's really easy. I'm just going to steal. It's going to be temporary because I already know I don't want to have the same piece always, but for now, just to get a little ego boost with having accomplished something, I will just steal this definition and we will call it fresh piece. And we put it here. Position 5 board height. Oh, looks all good. Or we can spice it up and instead of the T piece, we spawn, I don't know, what other pieces did we have? T piece equals, let's go to the top. Where are our piece definitions? Ah, there it was. We can use the J piece, or the J piece is the only other one that we have. So let's just use this. Oh, and it's blue. Oh man, if that works, that will already feel like much more like Tetris. So let's make sure this compiles. Compiled without errors. Oh my boy. And now do I have to reload? Interesting. Now nothing is happening. So I guess I broke the drop function. If can drop, then to the drop. Why doesn't it work? So just some lazy boy debugging here. I will have both branches execute the same code again. And now it works again. So that tells me it's actually going into the else branch. So can drop is false. Interesting. Okay, so let's do it's an excellent opportunity to show some of the debugging tools available to us in Elm. Let's do the good old. I have a hunch. Yeah, let's just do this. We'll put out the result of mapping the isEmpty function over our absolute type positions. So can drop, and like again, I just, for people who haven't watched the episode where I explained it, I was about to write this little fancy arrow here again, but I just write out what it actually does, and then it's hopefully shows why this is nothing to be scared of. So what I want to write is map isEmpty absolute type positions, and because so this other function composition element, you might call it, that I'm using here is just, if I write it like this, I basically can remove the parentheses, and it reads a bit more like a flow than this, like, oh, the parentheses open, where does it close? Like it's a bit nicer. Like, and you can chain multiple things like this, like especially if you have a chain of where you always pass in the result to the next function, and this reads really nicely and over these nested parentheses. Cool. So I'm going to save this. It does not compile because I have still my debugging expression here. So let's write again what we initially wanted to have working. It's compiling, and we bring up the console and we increase the font size, and we see like, okay, it's really not all have true. It's rather the opposite. All the tiles that we want to have after we dropped it are not empty. So why is that the case? Well, the case it's because our piece is not even visible. Like I think just to have the feeling of it dropping in, I placed it over the last line here, or the last row, I should say, in our terminology. So that means at least one of those pieces I'm trying to drop them into, no, all of them, is even after they're dropped, they're still outside of the board. That's why they're not empty, and that's why I cannot drop the tile. So that's what it's happening. So I think my quick hack for this would be, instead of, I mean, we see already here also where we're trying to do this, instead of dropping it on top of our board, I'm dropping it 2 rows below. And I have to look the same code up in the init function. So here we say board height -2, and I hope with that our piece actually spawns on our board and is able to drop again. And now we see, oh, that's also interesting. True, false, true, false, true, false. I wonder what's happening there. No, I don't know. I don't know how this now can ever be false. Do I have to reload? Yeah, okay. I know, I know, because these, actually that's a problem with my hot code replacement, because we are now binding, like with our timer function or timeout function that we are binding. Oh, look at this. Isn't that beauty? It spawned the L. But I mean, there's still a bug. But I just finished my quick explanation of why I had to hard reload, is because we're now registering global callbacks, like the timeout function. So when my hot code replacement thingy loads, it apparently it doesn't unregister the timeout call we did before. So it was still calling the previous version of our code. Okay, cool. The L is dropping, but then something, the place tile on board thing doesn't really work. So I'm a bit confused, but we'll find this out eventually as well. So first we can remove this old debugging function. So that's cool. So board equals, so this part is not working, and I'm not sure why. Let's jump into the definition. Yeah, that's the function that we already used to render, like to pretend the piece was already baked on the board. But why does it not work? Current piece translate, min-row taken. I mean that, well, it does work for rendering the board with the current piece, and now I'm confused why it doesn't work. Okay, let's just okay, so even in our else branches of our if statements, we can have let in blocks with local expressions. And I mean, I could obviously also just put something in here, but usually it's good practice to keep the let in blocks like the definitions for that and the block close to where we actually need this. I mean, for the debugging, it doesn't really matter because it's going to be removed eventually, but it lets us avoid unnecessary calculations if we have a local let block, for example, to the else block, because then this expression will only be calculated when we actually execute the else branch. Otherwise, if I put it up here with the other expression, then it will be calculated every time. So let's, I don't know, maybe that's a bit too optimistic to debug the whole board, but I'm just curious how it looks. So what I'm trying to have a look at is when our first tile our first piece is dropped and we come to the conclusion we should bake it into the board and render this or execute this branch of this if statement. I also want to just see what, I mean, I have a hunch what we're assigning, which is still an empty board, but I just want to see it myself because I cannot believe it. Let's reload here and just wait for this T piece to hit the bottom. Also, this gives me some more time to think what potentially could have gone wrong, or what actually went wrong probably. And here we go. Yeah, it's pretty much what I expected. It's a row and they are all empty. So why does it happen? So actually, so what I should probably rather output is the current piece. Yeah, I will. Let's see how we can debug this. I mean, also worth mentioning, there's an excellent test library or infrastructure to write tests for Elm. So the proper way to do this now would probably to write a test that makes sure if I take this current board that I have and this current piece, I mean, they're all just values. So I will abuse my production code, so to speak, to test this. But the proper way would be to write a test. I haven't set up the test stuff, and I have to admit I'm also not super familiar with it. But actually, I'm always looking for toppings while I stream to go into detail in my show notes or the write-up for my blog. So I promise hereby I will tackle I will show how I would have written a test for this. It's an example. It's an excellent forcing function for me to set up testing, and I will do this for this project after I finish today's episode, and then we can just have it ready to go when we start streaming. When I start streaming next week, and I will just write a bit up if I see something that's weird in my blog post after this. Cool. So actually, I don't want to see the board. I want to see the current piece, and I want to know why it is not being baked in. So let's rather current ops piece. So I just want to output. I just wanted to output the current piece so I can copy the definition or translate. I don't know how it's going to be formatted, but I just want to imitate this object in a constant in my code, and then I just want to call the function directly and see what's what. Current piece. Okay, tiles. Yeah, that's about what I would have expected. So let's move this over here, and I think I will go just debug in closeness to my init function. So borked current piece. What's the type definition for current piece? And there's a lot of things called current piece in my code currently. Current piece, here we go. So let's make sure this I mean, this is, yeah, it's actually pretty much directly usable, I guess. Color is red, position is 520. Whoops. Tiles are that. So let's see, can I save this? Does it compile? It compiles. So here's my way I want to quick and dirty debug this. So I just want to render the result of the place piece on board function in my initial board state. So instead of empty board, I'm just going to write it because it's becomes much more clearer this way. Place piece on board, board current piece, empty board. And I'm going to unregister our subscription so that the timer function doesn't mess up the result of this calculation. Sub none, so our keys also won't work. Compiles, wonderful, hard reload. Interesting. Ah yeah, okay, of course. So this is actually the T piece that we are seeing. That's the new piece, or the actual current piece. Yeah, let's close one of those windows in it. So yeah, like we haven't defined a state where we can have not a current piece, so we will always see this current piece. But if we go back to the definition, position 520. Well, actually, let's change this color to blue. And this new piece, I will just break this and make sure this current piece is somewhere out of sight. Okay, let's reload this. So now we're closer to the state that we want to investigate, which is we have placed the board current piece on the empty board. But also, why is current piece position 520? We decided that the lowest row is the row with the index 0, or the row number 0. So I don't understand. Okay, so if we change this to 5, it places it successfully, so that's good. The actual question is, if we go back to, so that's the problem. So the problem is the position that we're trying to place is at row 20, which is wrong, because also we know it's out of sight. So that's also the reason why we don't see it. So we can actually remove and undo our little debug code here. Going to reinstate this. So now we should see again. And we have to revive our subscription. There we go. Here you go away. I cannot very bulk current piece. That is correct. Borked. This should only be the empty port again. So now we are back to our state where when the piece drops, it doesn't render on the board. So where was that? Place piece on board. It's here. So current piece. Oh yeah, actually I could have seen this right away. Let's confirm that the piece that gets locked here has the bad row number 20. And yes, it has. So where does this current piece come from? It's the current piece. So it's like the current from the current state of our model. So that's good. I have a hunch. So this is definitely wrong. It's my little hack that I introduced to. So the drop piece of course should not already reset it to the top location, which is okay. It's just right. Yet you get hit in the face by your own hacks. So I have a good hunch. Oh, where is our key handler is still working? Yes. So that's wonderful. Maybe not drop it in the. And this the outputs are still the outputs from the previous. It's not working. Okay. Tonight is tough. That's why people are afraid of live coding, because it's those gnarly, stupid errors that you introduce yourself that make you look stupid. But it's part of the game, so also a good experience to share, I guess. Did I reload? Let's reload. And I think I'm just current piece. Let's just wait. I think we never end up in this state for some reason, in this branch of the if statement. I could also decrease the time a bit, yeah, for the pieces to drop quicker. Like we never saw this debug statement, so that basically means can drop is always true, which is not good. Can drop is empty, absolute type positions and absolute type positions. Absolute type positions is overdropped piece. Okay. I'll just do something again. I'm doing the bad way of debugging. Instead of writing proper test, I will just write a debug statement that puts out some of our test or our function calculation results to manually verify the result. So I would say if, like, what I have the hunch, like the whole intention of this maybe nothing thing here was that if we yeah, sometimes it's like it's good rubber ducking. Is this, I don't know if you, is this actually a thing? Rubber ducking coding, rubber duck debugging is a method of debugging code and yeah, is a practice where the programmer would carry out around a rubber duck and debug their code by forcing themselves to explain it. So thanks for being my rubber duck, I guess, because I think we're trying to get to our significant row by dropping the insignificant rows. So if our position is 0 or negative, then we're not dropping anything, obviously. So that's not good. So that means basically we can say we can have maybe field, I would say if ty is smaller than 0, then we can definitely return nothing. So if the y component in our position of the current piece is below 0, then we are definitely not on an empty field there. So I'll just put this in here. Yeah, interesting. Probably should do something for the x, for the column as well. Ah yeah, actually field, I can even put it in here as well. If tx is smaller than 0, like on the other bound, the problem is not that complicated, because if we drop too many columns or row, then we'll just get head from nothing. So that's no biggie. Does it fix that already? Let's see. It compiles. Ah yeah. Get a nice break because the tiles drop so slowly. Yeah, nearly, I would say. Nearly. Okay, first I will just decrease these 1000 milliseconds to, I don't know, maybe 300. Okay, cool. That drops faster. It drops one, classic one by one, off by one, I would say. Let's see if this looks the same for the blue piece. Yes. But now it's also the question, if I try to drop it on top of the T, what happens? Ah yeah, it really looks like an off by one. Okay, so let us fix this. If can drop, it drops. But why? Translate tile, absolute table, that looks good, that looks good. Oh yeah, I think we have to drop one less, because otherwise we drop the significant row as well. And the same thing is here with the columns. No! Damn it. Why does it? Why does it? It shouldn't. It's also funny that, oh, it's only off in the on the lowest row. So I call this a partial success. Cool. Is empty, can drop. Ah, maybe actually I just one thing is off, either the rendering of the board, like maybe we're also just not rendering the last row. Well, row view, field forward, SVG, board view. Yeah, I think I call it a night for today. And yeah, as I said, I will, in my follow-up, I will start looking up how to properly set up the Elm test environment, write a bit about this, and then also in the next episode I will do my homework and show a first few tests to look into, and hopefully that will also help me identify what I'm not seeing here tonight. But yeah, it's been over an hour and I wanted to keep this series in nice digestible chunks, so I call it a day for today. Thanks for watching and see you next time.